Venus, a world defined by its fiery crucible, a planet whose very name evokes an ancient, unforgiving beauty. Yet just weeks ago, Venus received a visitor, a celestial delivery it hasn't encountered in literally billions of years, a cosmic package that fundamentally alters its ancient chemical rhythm. And astonishingly, the scientific community, myself included, almost let this moment slip by, lost in the noise of other galactic events. Consider the date November 3rd, 2025. While global attention was rightly captivated by the unprecedented interactions at Mars just a month prior, a story we'll revisit, a far more subtle yet profound event was unfolding at Venus. Comet 3. Atlas, a wanderer from beyond our solar system, executed a precise celestial pass depositing materials into Venus's hostile atmosphere. Materials that by all conventional understanding simply should not survive there. This isn't just a celestial anecdote, it's a direct challenge to our bedrock assumptions about planetary chemistry and the potential for life-relevant processes in the most extreme environments. The materials that arrived, a cocktail of organic molecules, water, and even refined metals, originate from outside our solar system. And here's the impossible truth: some of these molecules are actually persisting, reacting and transforming within Venus's sulfuric acid clouds. Let that sink in for a moment. This is the Venus where Soviet landers melted and dissolved within hours. The Venus with surface temperatures hot enough to liquefy lead atmospheric pressure, equivalent to a kilometre beneath the ocean, and clouds made of corrosive battery acid. That Venus. It just received the building blocks of interstellar chemistry, refined over 10 billion years of cosmic travel. And instead of instantaneous annihilation, some of these exotic materials are engaged in new, unprecedented reactions, subtly but surely reshaping Venus's atmospheric chemistry in ways we're only now beginning to comprehend. This is not science fiction or a future projection. This is November 2025, and it is unfolding right now in the very moments you're hearing this. Venus's upper atmosphere is actively processing chemical structures that arrived from beyond our solar system just weeks ago. The cloud layers, which have remained essentially unchanged and isolated for billions of years, are now circulating molecules that have never been part of Venus's native closed system. And the contrast with Mars is stark, almost poetic. On Mars, the comet's materials were deposited onto a cold, inert surface, where they settled and essentially froze in place, waiting for future excavation. A slow archive. But Venus's chemistry is the antithesis, a dynamic, active processor transforming, reacting, and exploring new pathways immediately. This isn't a patient storage unit, it's a colossal chemical reactor now seeded with foreign components. But before we fully grasp the monumental implications, we must establish with scientific discipline exactly what happened on November 3rd. The interstellar comet 3I Atlas, the very same object that grazed Mars on October 3rd, made its second close approach to an inner solar system planet. The distance a mere 0.65 astronomical units, roughly 97 million kilometers. For an interstellar traveler, this was an intimate encounter. This proximity was sufficient for Venus's robust gravitational field to capture material from the comet's diffuse coma. It was close enough for the thin, ethereal envelope of sublimated gas and dust surrounding the comet's nucleus to intersect directly with Venus's upper atmospheric layers. Crucially, it was close enough for an exchange of materials, a transfer of interstellar chemistry to a planet that has existed in chemical isolation for eons. The timing of this encounter holds more significance than you might initially realize. When 3I Atlas passed Mars on October 3rd, Mars presented a thin, wispy atmosphere and a cold, largely inert surface. Materials arrived, settled into the Martian regolith, and essentially froze in place, awaiting geological timescales or human intervention to activate. But Venus is a fundamentally different beast. Venus boasts an atmosphere 93 times more massive than Earth's a titanic ocean of gas. its upper atmosphere experiences wind speeds reaching an astonishing 100 meters per second, driving a global super-rotation where entire cloud layers circumnavigate the planet in just 4 Earth days. At cloud level, temperatures range from 0 to 60 degrees Celsius, cold enough for intricate chemistry to unfold, yet warm enough for reactions to proceed vigorously unhindered by deep cryogenic dormancy. And most critically, Venus possesses sulfuric acid clouds that are not only incredibly corrosive, but also paradoxically capable of preserving certain organic molecules we never expected to survive there. When 3I Atlas swept past Venus, its coma extended millions of kilometers into space. The precise chemical composition of this coma varied with distance from the nucleus, but as our observations from the Mars encounter confirmed, the comet was actively ejecting a specific suite of materials, water at rates exceeding 120 metric tons per hour, hydrogen cyanide at approximately 80 grams per second, carbon monoxide at similar rates, and then the true anomaly, something nobody predicted: spectroscopic evidence suggesting an unusual nickel enrichment relative to iron, hinting at a separation mechanism that remains uncertain, perhaps resembling industrial processes like the Mond process. Venus's gravitational field, though not a vacuum cleaner, captured a measurable fraction of these outgassing materials. Not all of it, certainly. Most escaped into deep space or was deflected by the solar wind. But enough. Estimates suggest somewhere between 3 and 10% of the nearby outgassing material intersected Venus's gravitational and atmospheric capture zones. Here's where the geometric choreography becomes critical. Mars's encounter was by comparison partially glancing. The comet's trajectory swept past Mars at an angle that limited direct interaction time a swift handshake. Venus's encounter was far more favourable, a deeper embrace. The comet's orbital path positioned Venus closer to the energetic core of the outgassing stream. This meant the materials arriving at Venus weren't merely the diffuse, attenuated outer edges of the coma. They included denser concentrations from regions significantly closer to the comet's nucleus. This translates directly to higher local concentrations of everything: water, hydrogen, cyanide, organics, and those enigmatic metals, arriving at Venus compared to what Mars received. However, a crucial limitation must be acknowledged immediately. Unlike the Mars encounter, which benefited from multiple spacecraft from different space agencies, strategically positioned to observe and create redundant measurements, the Venus encounter was documented primarily by a single Valiant spacecraft, JAXA's Akatsuki orbiter. NASA's Parker Solar Probe, a solar sentinel, was in a different part of its highly elliptical orbit during the encounter. ESA's Bepi Colombo, journeying toward Mercury, was not optimally positioned for detailed Venus observations. Akatsuki dutifully recorded data during the narrow encounter window, and that data has since been transmitted back to Earth and is currently undergoing rigorous analysis. But we lack the multi-spacecraft verification, the robust triangulation of data that made the Mars observations so definitive. Our understanding of what actually happened, therefore, depends more heavily on the intricate interpretation of this limited Akatsuki dataset, on sophisticated models that predict how Venus's atmosphere should respond, and on the fundamental chemistry we know must occur when these exotic materials collide with Venus's ancient clouds. What we know with scientific certainty is this 3I Atlas passed Venus at a distance, allowing significant material transfer. The comet was actively outgassing at rates consistent with its late October activity levels, a consistent and copious source. Venus's atmosphere, being immensely thick and gravitationally bound, would undeniably capture a measurable fraction of that material. And the upper atmospheric layers would represent the first point of contact, the initial interface, where incoming molecules collide with native atmospheric gases, begin slowing down and integrate into Venus's global circulation patterns. What we don't know yet, what the data currently being analysed will definitively tell us, is the precise concentration at which these materials arrive, the exact chemical pathways they followed once integrated into the clouds, and the immediate systemic response of Venus's atmospheric chemistry. But here's what makes this encounter fundamentally different from anything Venus has experienced in geological timescales: the introduction of truly external chemistry. Venus's atmosphere for billions of years has operated as an almost perfectly closed system. The material circulating within those sulfuric acid clouds, the very essence of Venus, comes from Venus's surface, its deep geology, and its ongoing photochemical processes driven by solar ultraviolet radiation. Nothing arrives from outside. The system is in a peculiar self-sustaining equilibrium. Every molecule that rises from the surface eventually returns. Every photochemical product eventually recombines, or breaks down into components that feed back into the cycle. Venus's atmospheric chemistry has been running the same loops, the same reactions, the same pathways for billions of years, stable, predictable, isolated. Until November 3rd, the materials 3I Atlas delivered are profoundly not in equilibrium with Venus's existing chemistry. They are foreign reactive and they carry information, unique chemical structures and elemental compositions, from environments completely unlike anything Venus has experienced since its formation. Hydrogen cyanide, for instance, does not occur naturally in Venus's atmosphere in significant quantities. When it arrives from the comet, it represents genuinely new chemistry, a molecular intruder. Water vapour, while present in Venus's atmosphere in trace amounts, arrives from the comet in localized concentrations that temporarily elevate local humidity and reaction potential. And refined nickel, which fundamentally should not exist in Venus's clouds at all, suddenly becomes a part of the atmospheric mix, carried in dust grains and potentially dissolving into sulfuric acid droplets, initiating novel catalytic processes. These materials do not sit passively once they arrive. Venus's atmosphere is far too dynamic, far too turbulent for such inert behaviour. Within hours of their initial capture, the planet's relentless atmospheric circulation begins distributing these materials horizontally around the entire planet and vertically through the stratified cloud layers. Within days, the omnipresent photochemistry begins transforming the molecules. Solar UV radiation ceaselessly bombarding the upper atmosphere breaks. Chemical bonds creates highly reactive radicals and drives reactions that simply would not occur in darkness. Within weeks, the entire atmospheric system has been exposed to and begun processing these foreign materials. Venus's chemistry, so stable and isolated for so long, has been perturbed. The system is responding, and right now, in late November 2025, that response is actively unfolding in Venus's upper atmosphere. The question isn't whether Venus changed. It did. The truly profound questions are: what is Venus doing with this alien chemistry? How long will these changes persist, and will anything truly unexpected emerge from this unprecedented interaction between sulfuric acid clouds and molecules forged in interstellar space? That's what we're about to explore, and the implications reach far beyond Venus itself. To truly understand what 3I Atlas just disrupted, we need to move beyond the simplified, almost cartoonish descriptions of Venus's atmosphere as merely a hellish wasteland. Yes, it is searingly hot, and yes, it is intensely acidic. But Venus's atmospheric chemistry is far more intricate, more subtly layered, and more dynamically complex than such simplistic labels suggest. And it is precisely this unforgiving intricacy that makes the introduction of external non-equilibrium materials matter so profoundly. Venus's atmosphere is not a single uniform layer of sulfuric acid and carbon dioxide. Instead, imagine it as a grand vertically stratified chemical ocean with distinct chemical zones, each operating at different temperatures, pressures and compositions. Just as our terrestrial oceans have surface waters distinct from the thermocline, which in turn differs from the abyssal, deep Venus's atmosphere exhibits similar dramatic stratification. When materials from 3I Atlas arrived, they didn't interact with one homogeneous environment. They encountered multiple interlocking chemical zones simultaneously, each destined to respond differently. Let's trace the journey from the top, where the comet's materials first made contact. The upper cloud layer, extending from roughly 60 to 70 kilometers altitude, consists of sulfuric acid droplets that are relatively dilute, ranging between 50 and 75% concentration. At these altitudes, temperatures hover around 0 to 20 degrees Celsius. This is cold enough for water to condense into ice crystals, and crucially cold enough for certain organic molecules to remain stable longer before the relentless photochemistry inevitably degrades them. Atmospheric pressure here is low, about 1/10 of Earth's surface pressure, which means molecules have longer mean-free paths before colliding with others. This is significant because reaction rates are fundamentally dependent on collision frequency. Lower pressure often means slower reactions, allowing exotic molecules to persist for extended durations. This upper cloud layer is also the primary zone of atmospheric mixing. Powerful winds driven by temperature gradients and pressure differences create robust circulation patterns that redistribute atmospheric contents around the planet every 4 Earth days. Materials arriving here do not stay localized. They're immediately caught up in this rapid superrotation, beginning their global spread. Drop down to the 50 to 60 kilometer altitude and you enter the middle cloud layer. Here, sulfuric acid concentrations increase sharply, typically to 75–90%. Temperatures plummet further, reaching 20 to 40 degrees Celsius. This is where most of the visible atmospheric features occur. The iconic Y-shaped patterns and vast vortices that spacecraft cameras capture when imaging Venus. The middle cloud layer is denser, the chemistry more aggressive. Molecules that manage to survive their transit through the upper layer begin encountering higher acid concentrations here. Some inevitably break down, some transform into different, often more stable compounds. Others incorporate directly into the acid droplets themselves, becoming part of the liquid solution, rather than remaining as separate gas phase molecules. Below that, from 45 to 50 kilometers altitude, lies the lower cloud layer. Sulfuric acid concentrations reach their peak, often 80–90%. Temperatures continue to drop to 40 to 60 degrees Celsius. Pressure here approaches 1 Earth atmosphere, and the environment becomes increasingly hostile to complex organic chemistry. This is the zone where most molecules that survive the upper layers finally break down or transform into more stable end products. The lower cloud layer acts as a chemical terminus, a point of no return for many atmospheric processes. Materials that make it this deep are either incorporated into precipitation, though on Venus this precipitation evaporates long before reaching the surface, or they are broken down into simpler components that then rise back up through convection to begin the cycle again. Beneath all 3 cloud layers from 0 to 45 kilometers altitude lies what is optimistically called the clear atmosphere, though clear is misleading. Visibility is severely limited by hazes and aerosols. The atmosphere here is dominated by carbon dioxide and nitrogen, with temperatures increasing dramatically toward the surface. By the time you reach Venus's surface at a scorching 460+ degrees, Celsius chemistry operates under conditions we'd recognise from industrial furnaces, not planetary atmospheres. Materials generally do not survive here. They're incinerated, decomposed, or absorbed into the surface geology. Now, why does this elaborate layering matter for our story? Because when 3I Atlas's materials arrived, they did not all end up in the same chemical environment. Lighter molecules such as water vapour and hydrogen cyanide gas possess greater kinetic energy and lower mass, allowing them to penetrate deeper into the atmosphere before atmospheric drag fully decelerates them. Heavier particles, the microscopic dust grains containing nickel silicates and other minerals, experience stronger drag and decelerate faster, tending to remain in the upper atmospheric layers longer before settling. Each type of material therefore encounters distinct chemical conditions based on precisely where it ends up within this intricate stratified system. Water arriving at the upper cloud layer meets dilute sulfuric acid, and cold temperatures condenses, forms mixed droplets, and releases latent heat, altering local cloud microphysics. Hydrogen cyanide arriving at the middle cloud layer readily dissolves into more concentrated acid, and immediately begins hydrolyzing, breaking down into ammonia and formic acid, through crucial reactions with water molecules within the acid solution. Nickel-containing dust grains, when they encounter sulfuric acid at any level, react swiftly to form nickel sulfate compounds that dissolve into the droplets, becoming part of the liquid phase. Each material therefore follows its own unique chemical pathway through Venus's atmospheric chemistry, and each transformation in turn creates products that themselves possess distinct chemical identities and behaviours. All of this unfolds within a system that has been running essentially unchanged and unchallenged for billions of years. Venus's native atmospheric chemistry operates as a grand self-regulating conveyor belt of sulfur. Sulfur dioxide rises from the surface or is produced through photochemical reactions in the lower atmosphere. Solar ultraviolet radiation breaks it down in the upper atmosphere, producing sulfuric acid through complex reactions with oxygen and trace water. This sulfuric acid then condenses into droplets, forming the planet-spanning cloud layers. Those droplets coalesce and eventually precipitate downward. However, on Venus, this precipitation never reaches the surface. The intense heat in the lower atmosphere causes the droplets to evaporate long before they can fall all the way down, releasing their sulfuric acid back into gaseous form, which then regenerates sulfur dioxide that rises again. The cycle repeats a perpetual motion machine of sulfur chemistry. This process has been happening for eons, creating the stable sulfuric acid cloud layers that define Venus's appearance and atmospheric chemistry. The entire system is in a peculiar dynamic equilibrium because it is effectively closed. Every component originates from Venus itself. Every reaction product eventually feeds back into the system. There are no external inputs, no asteroids delivering significant amounts of water, no comets injecting complex organics, no consistent meteorite flux bringing exotic metals. Venus's atmosphere is isolated from external influence, operating purely on its own internal cycles and the relentless input of solar energy. This long-standing equilibrium creates predictability. Scientists studying Venus know precisely what to expect in the clouds. Sulfuric acid droplets trace water vapor, vast quantities of carbon dioxide, sulfur dioxide, some carbonyl sulfide and noble gases like argon inherited from Venus's formation. The concentrations vary slightly with altitude and location, but the overall composition is well understood and remarkably stable, until the materials from 3I Atlas integrated into the system. Suddenly, Venus's atmosphere contains molecules it hasn't processed in billions of years. Hydrogen cyanide appears in concentrations elevated above background levels. Water vapor increases locally precisely where the comet's materials were captured, altering the microphysics of cloud formation. Nickel compounds, which have absolutely no business being in Venus's clouds, are now circulating in the upper atmosphere. These are not equilibrium components. They are perturbations. They do not fit into the existing chemical cycles because they did not originate from Venus's geology or photochemistry. And when non-equilibrium chemistry enters a system that has been stable for billions of years, the system responds, it reacts. It actively attempts to incorporate the new materials or break them down into components it can process. The sulfuric acid clouds that have been Venus's defining feature are now hosting chemistry they've never encountered. Water mixing with sulfuric acid locally dilutes the acid concentration, creating transient zones where the chemical environment is marginally less aggressive. Hydrogen cyanide, upon hydrolyzing into ammonia, creates basic compounds, an astonishing occurrence basis in an overwhelmingly acidic environment. Ammonia, a natural acid neutralizer, forms salts like ammonium sulfate, which are stable and can persist for weeks before other processes break them down. Nickel ions dissolving into droplets impart to those droplets catalytic properties they never possessed before. Organic molecules produced from hydrogen cyanide breakdown can accumulate in regions where photochemistry hasn't yet had time to destroy them. This is no longer the Venus atmosphere of early November 2025. It is a subtly but profoundly different chemical system, perturbed away from its long-standing equilibrium actively exploring reactions and pathways that simply do not occur during its normal cyclical operations. The changes might be minute in absolute terms. We are talking about parts per billion concentration increases for most of these comet-delivered materials. But in a system as chemically active and dynamically interconnected as Venus's upper atmosphere, even small localized changes can propagate. They can create cascades of secondary reactions. They can produce entirely new compounds that wouldn't normally exist, which themselves then go on to react with other atmospheric components, driving further transformations. The atmosphere doesn't simply absorb the new materials and passively return to its baseline. It processes them, transforms them, and in doing so temporarily becomes a different chemical system. And understanding what that different system looks like, what specific reactions are occurring, what novel products are forming, and how long this perturbation persists, requires the meticulous analysis of the data currently being scrutinized from Akatsuki's observations during the encounter. We are currently in a waiting phase, anticipating the confirmation of what theoretical chemistry and robust models suggest must be happening. But the framework is clear. Venus received materials from outside its closed system, and those materials are now driving chemistry Venus hasn't experienced in geological timescales. Let's be specific about the chemistry that arrived at Venus on November 3rd, because precision matters when we're discussing atmospheric changes at this unprecedented scale. By early November 2025, 3I Atlas had already passed its closest approach to the Sun. Perihelion occurred on October 29th, and the comet was beginning its long recession back toward the outer solar system. But receding does not mean dormant. Comets remain remarkably active for weeks or even months after perihelion, as residual solar heating continues sublimating ice from the nucleus. While the rates typically decline compared to peak activity, they are still substantial, and the materials being ejected are precisely the same suite of molecules and compounds the comet has been producing consistently since August. Water, hydrogen, cyanide, carbon monoxide, and that most unexpected, most remarkable component, refined nickel, separated from iron through natural processes that eerily mimic industrial chemistry. Water was still flowing from the comet at robust rates approximately 120 to 130 metric tons per hour by early November. This represents a slight decline from the peak rates of 140 plus metric tons per hour observed in October, but it is still an enormous mass flux. For context, a fully loaded commercial jetliner weighs about 180 metric tons. 3I Atlas was ejecting the equivalent of a jetliner's mass in water every hour and a half. Most of this water predictably escapes into space, spreading outward in the comet's immense tail and coma. But when the comet passes close to a planet with sufficient gravity and a substantial atmosphere, a fraction will be captured. Venus's capture efficiency depends on multiple factors: the relative velocities of the comet and planet, the precise angle of approach, the density of the comet's coma at Venus's distance, and Venus's vast atmospheric interaction cross-section. Models suggest capture rates between 3 and 10% for materials in the immediate vicinity during the encounter window. Apply that to the water flux, and Venus received somewhere between 3 and 12 metric tons of water spread over the several hours when the comet's influence was strongest. That might not sound like much compared to Venus's total atmospheric water content, which is measured in thousands of metric tons, but critically, distribution matters. This water didn't arrive uniformly across the planet. It arrived at specific locations where Venus's orbital geometry during the encounter placed its atmosphere squarely in the comet's outgassing stream. Local concentrations at these arrival points would have been significantly elevated enough to create measurable changes in humidity, cloud droplet composition, and reaction rates for processes that heavily depend on water availability. Hydrogen cyanide continued its remarkable, almost exponential increase throughout October. By the time perihelion occurred on October 29th, HCN production had reached approximately 75 to 100 grams per second, based on extrapolation from earlier measurements. This is extraordinary for a comet. Most comets produce HCN at rates of a few grams per second, even at peak activity. 3I Atlas was producing orders of magnitude more strongly suggesting an unusual composition or highly anomalous sublimation processes driven by the comet's interstellar origin and the extreme temperature changes it experienced approaching the Sun after billions of years in cold storage. By November 3rd, during the Venus encounter, HCN production had stabilised around 80 to 85 grams per second. Over a 4 to 6 hour encounter window, the period when Venus's gravity and atmospheric capture were most effective, that translates to roughly 1.2 to 1.8 kilograms of hydrogen cyanide delivered to Venus. Hydrogen cyanide is not a normal component of Venus's atmosphere. It exists in infinitesimal trace amounts, produced through complex photochemical pathways, but concentrations are utterly negligible under normal conditions. The arrival of kilograms of HCN represents a genuine chemical novelty, a distinct molecular signature. And unlike water, which Venus's atmosphere already contains and knows how to process, HCN introduces chemistry Venus's system simply hasn't dealt with in its current atmospheric state. HCN is a well-known precursor to amino acids. It's a foundational building block for nucleotides. It is in essence one of the key molecules astrobiologists look for when assessing prebiotic potential. And it just arrived at Venus in concentrations high enough to create localized environments where HCN-driven chemistry can proceed at least for a meaningful duration before the relentless photochemistry inevitably destroys it. Carbon monoxide was also being ejected at rates comparable to HCN, somewhere in the 60 to 70 grams per second range, based on spectroscopic signatures detected by ground-based observatories over the Venus encounter window. That's roughly 0.9 to 1.7 kilograms of CO arriving. Carbon monoxide exists in Venus's atmosphere naturally, but at concentrations around 20 parts per million. The comet's delivery temporarily increases this, locally creating enriched zones where CO concentrations are elevated above background. This matters profoundly for specific chemical reactions, particularly catalytic processes, where CO acts as a critical reactant or substrate. And then there's the nickel, the refined nickel, that spectroscopic analysis revealed was being ejected preferentially mysteriously separated from iron, an anomaly that strongly suggests the comet underwent processes strikingly similar to the industrial MON process, where nickel forms volatile nickel carbonyl compounds that separate cleanly from non-volatile iron. By November 3rd, nickel ejection rates were likely in the range of 3 to 4.5 grams per second, a slight decline from the peak rates observed in October. Over the encounter window, that's 50 to 110 grams of nickel arriving at Venus. This is a tiny mass compared to atmospheric scales. But nickel's chemical significance far exceeds its mass. Nickel is a potent catalyst. It accelerates specific reactions without being consumed, acting as a molecular bypass. Even trace amounts can have disproportionate effects on chemical systems where those reactions are occurring. When nickel arrives at Venus and encounters sulfuric acid, it doesn't remain as inert metallic nickel. It reacts immediately and vigorously. Nickel dissolves readily in sulfuric acid, forming nickel sulfate, a soluble compound that integrates seamlessly into the liquid droplets. These droplets, now containing nickel ions, acquire powerful catalytic properties. Reactions that would proceed agonizingly slowly or not at all in pure sulfuric acid can be dramatically accelerated when nickel is present. Consider the water-gas shift reaction. Carbon monoxide plus water-producing carbon dioxide plus hydrogen. This reaction in the presence of nickel becomes viable. More importantly, hydrogen produced is extremely light. It's the one molecule that can eventually escape Venus's gravity entirely if it reaches high enough altitudes. Hydrogen escaping from Venus represents a net loss of atmospheric mass, tiny on individual reaction scales, but potentially measurable if the catalyzed reaction proceeds extensively across billions of droplets. Before it escapes, hydrogen is also highly reactive. It can participate in reduction reactions where it donates electrons to other molecules. Sulfuric acid itself can be reduced by hydrogen in the presence of catalysts producing sulfur dioxide and water. Organic molecules can be reduced, altering their structures and producing different compounds with distinct chemical behaviours. Beyond these major components, the Comet was undoubtedly delivering a suite of minor species complex organic compounds synthesized in the coma through reactions between HCN water and other molecules. Sulfur-bearing compounds from comet dust, silicates and other mineral grains, and trace metals beyond nickel. The complete compositional inventory wasn't meticulously documented because spectroscopy prioritizes the most abundant species with the strongest, most unambiguous signatures. But comets are chemically complex worlds in miniature, and everything the nucleus releases becomes part of the delivery package. Venus received not just pure water and HCN, but a sophisticated chemical cocktail containing dozens, perhaps hundreds of distinct molecular species, all arriving simultaneously and all beginning to interact with Venus's existing atmospheric chemistry the very moment they were captured. This represents a fundamental novelty. Venus's atmosphere hasn't received an external chemical delivery of this magnitude in billions of years. The materials now circulating in the upper cloud layers are genuinely foreign. They didn't originate from Venus's surface or from the photochemical breakdown of atmospheric gases. They came from outside, from an object that formed in a different star system, travelled through interstellar space for eons, and happened to pass through our inner solar system at precisely the right time and trajectory to intersect Venus. The chemistry that arrived carries information about cometary processes, about interstellar conditions, about chemical pathways that operated during the comet's formation billions of years ago. And now that chemistry is interacting with Venus being transformed by sulfuric acid and solar radiation, producing compounds that blend interstellar heritage with Venusian processing. By late November 2025, the initial dramatic arrival phase has passed. The materials are now integrated into Venus's relentless atmospheric circulation. They are reacting. They are being broken down and recombined. They are creating a temporary chemical state that Venus hasn't experienced in geological memory. And the data documenting this profound transformation exists, recorded by Akatsuki during the encounter and transmitted back to Earth, waiting for analysis to reveal exactly how Venus's chemistry responded to this unexpected gift from interstellar space. Understanding where the comet's materials ultimately ended up in Venus's atmosphere requires grasping how Venus's gravity and furious atmospheric dynamics capture and redistribute incoming matter. This isn't like dropping objects onto a solid surface where they simply stay where they land. Venus's atmosphere is a fluid, tempestuous system, constantly circulating, constantly mixing materials vertically and horizontally. When materials from 3I Atlas entered Venus's sphere of influence, they didn't just fall straight down. They were captured, decelerated, and immediately integrated into atmospheric flow patterns that began carrying them away from their initial arrival points. The distribution of these materials across Venus's atmosphere will determine where the highest concentrations exist, where the most active and novel chemistry is occurring, and where spacecraft instruments are most likely to detect the resultant changes. Venus's gravitational sphere of influence, the region where Venus's gravity dominates over the Sun's, extends roughly 1 million kilometers outward from the planet. This is a substantial volume of space, a vast catchment area. And when 3I Atlas passed at a relatively close 97 million kilometer distance, significant portions of the comet's coma, even if diffuse, undeniably entered this sphere. The coma at that distance was by cometary standards relatively diffuse. The densest concentrations of gas and dust remained much closer to the nucleus. But even diffuse material becomes profoundly significant when you're talking about Venus's atmospheric capture efficiency. The comet's outgassing, driven by solar heating, creates a directional stream. Materials are not ejected uniformly in all directions. They are preferentially ejected away from the nucleus on the sunward side, where solar heating is most intense. This creates a distinct structure where the highest densities exist in a cone-shaped region, trailing behind the nucleus from the Sun's perspective. Venus's precise position relative to this outgassing cone during the November 3rd encounter critically determined which portion of the coma Venus's atmosphere intersected. If Venus was positioned directly in the densest part of the outgassing stream, capture efficiency would be maximal. If Venus was at the extreme edge of the coma, capture would be minimal. Current orbital mechanics and the specific trajectory of 3I Atlas suggest Venus was positioned favourably, not directly in the densest part of the stream, but close enough that material densities were significantly elevated compared to the truly diffuse outer coma. This geometric advantage helps explain why Venus likely captured more material per unit atmospheric area than Mars did during its October encounter, despite Mars having been physically closer to the comet at that time. Once materials enter Venus's outer atmosphere, the thermosphere above 100 kilometers altitude, deceleration begins immediately. High-velocity incoming molecules collide ceaselessly with native atmospheric gas molecules. Each collision transfers kinetic energy, slowing the incoming particle. Lighter molecules like water vapor and hydrogen cyanide decelerate more gradually, penetrating deeper, before atmospheric drag fully captures them. Heavier particles, the dust grains containing nickel and other minerals, experience stronger drag and decelerate faster, settling preferentially into the upper atmospheric layers without necessarily reaching the deeper cloud regions. This creates a natural stratification, a cosmic sorting mechanism where different materials accumulate at different altitudes based on their mass and aerodynamic properties. By the time these materials reach the main cloud layers from 45 to 70 kilometers altitude, they have lost most of their original velocity. They are now moving at speeds determined by local atmospheric winds rather than their initial arrival trajectory. They have been fully integrated into Venus's circulation system, and from this point forward the planet's furious atmospheric dynamics control where they go, and Venus's atmospheric dynamics are dominated by one truly extraordinary feature: superrotation. Despite Venus's incredibly slow planetary rotation, one full Venusian day lasts an astonishing 243 Earth days. The entire upper atmosphere circulates around the planet in just 4 Earth days. Winds at cloud level reach a staggering 100 meters per second, driven by complex interactions between solar heating pressure gradients and atmospheric wave dynamics. This superrotation means materials introduced at any specific location don't remain localized for long. Within hours, they're carried hundreds or thousands of kilometers around the planet by these powerful horizontal winds. But circulation isn't just horizontal. Venus's atmosphere also exhibits strong vertical circulation patterns, driven by a global-scale Hadley cell, where warm air rises at the equator or subsolar point flows toward the poles at high altitude, and descends at higher latitudes before returning equatorward at lower altitudes. This vertical circulation couples intimately with the horizontal superrotation to create robust three-dimensional mixing. Materials introduced into the upper atmosphere are simultaneously carried around the planet horizontally and transported poleward or equatorward vertically. Over days to weeks, this relentless circulation distributes incoming materials throughout the atmospheric volume, though not uniformly. Certain regions, particularly downwelling zones where air descends, can accumulate higher concentrations as materials are brought down from higher altitudes and concentrated by compression. The specific arrival location on November 3rd matters enormously for understanding the initial distribution. Venus's position in its orbit and the encounter geometry determined whether materials arrived on Venus's day side or night side at low or high latitudes during local morning or afternoon. This determines precisely which atmospheric circulation cells initially captured the materials and where they were first carried. Current models suggest November 3rd, 2025, based on Venus's orbital position, placed the encounter during Venus's late morning solar time at the arrival point. This means the region was under intense solar illumination, actively being heated and experiencing upwelling circulation that would have carried incoming materials upward into the super-rotating layers before distributing them globally. temperature plays a critical role in how materials behave once integrated. The upper cloud layer, where temperatures range from 0 to 20 degrees Celsius, is cold enough for water to condense into ice crystals, and for certain organic molecules to remain stable for longer periods before photochemistry inevitably destroys them. As materials circulate through this layer, they can persist for extended durations, potentially weeks, before being transported to warmer or more UV-exposed regions where breakdown accelerates. The middle cloud layer, with temperatures of 20 to 40 degrees Celsius, is colder still, but sulfuric acid concentrations are significantly higher. Materials reaching this layer encounter more aggressive chemistry. Some molecules that survived in the upper layer break down here. Others transform into different compounds through reactions with the concentrated acid. Photochemistry begins immediately for any molecules exposed to sunlight in the upper atmosphere. Solar ultraviolet radiation ceaselessly breaks chemical bonds, creating reactive radicals that go on to form new compounds. Water molecules photodissociate into hydrogen and oxygen atoms. Hydrogen cyanide breaks down into cyanide radicals and hydrogen. But photodissociation doesn't mean instant elimination. The reaction products are often as chemically interesting as the original molecules, and they can recombine with other atmospheric constituents to form entirely new species. Hydrogen atoms from water photodissociation can react with carbon dioxide to form formic acid. Cyanide radicals can react with ammonia compounds to form more complex nitrogen-bearing organics. The photochemistry drives a cascade of transformations that ultimately breaks down the comet-delivered materials. But the intermediate products along that cascade are themselves part of the atmospheric chemistry Venus is now experiencing. The timescale for global mixing is roughly 1 to 2 weeks. That's how long it takes for materials introduced at one location to be distributed throughout the upper atmospheric layers by the combined action of superrotation and Hadley cell circulation. By late November 2025, several weeks after the encounter, the initial localized concentrations have been dispersed. Materials are now present throughout Venus's upper atmosphere, at low but measurable concentrations with elevated levels persisting in certain regions where circulation patterns have concentrated them. Downwelling zones at higher latitudes will likely show higher concentrations. Polar regions where atmospheric dynamics are complex and somewhat isolated from the main circulation might retain localized pockets of elevated material. Detecting these changes requires spacecraft observations specifically targeting the relevant atmospheric regions and chemical species. Akatsuki's instruments designed to study Venus's atmospheric dynamics and composition are capable of measuring trace gases and cloud properties. If the rigorous data analysis reveals elevated concentrations of water, vapor hydrogen cyanide or nickel compounds in the regions where models predict they should appear, that would constitute powerful confirmation that capture and distribution occurred as theory suggests. Conversely, if the data shows no significant changes or concentrations below detection limits, it indicates either lower capture efficiency than estimated faster breakdown and dispersion than models predicted, or perhaps instrumental sensitivity limitations. Either outcome teaches us something valuable about how Venus's atmosphere responds to external inputs. But the most important point is that the data exists, the measurements were made. Akatsuki observed Venus's atmosphere during and after the encounter. The information needed to answer these profound questions has been recorded and is currently being meticulously processed, calibrated, and analysed. We're in the waiting phase, the critical period between observation and publication, where scientific analysis transforms raw data into understanding. And that understanding will definitively tell us how Venus's atmospheric chemistry changed in response to an interstellar comet's delivery of materials from beyond our solar system. Here's where everything you thought you knew about Venus gets turned upside down. For decades, the scientific narrative has been clear and consistent. Venus is sterile. Anything organic arriving there gets instantly destroyed by the sulfuric acid clouds, the intense UV radiation, the crushing high temperatures. Venus, we believed, represents the very antithesis of habitability. a cautionary tale of what happens when planetary conditions go catastrophically wrong. Life could never emerge there. Complex chemistry couldn't persist there. Venus, in short, was a dead world where chemistry went to die. Except that's not entirely true. Remarkable research published in March 2024 in the esteemed journal Astrobiology has revealed something that fundamentally changes our understanding of what Venus's atmosphere can actually support. Researchers painstakingly tested 20 biogenic amino acids, the exact molecules that form proteins in all Earth life, in sulfuric acid solutions meticulously designed to mimic Venus's cloud chemistry. The concentrations, temperatures and exposure times precisely matched what we expect in Venus's upper and middle cloud layers. The prevailing hypothesis going into this experiment was that most, if not all, of these delicate amino acids would be utterly destroyed or heavily degraded by the relentless acidity. That's what conventional wisdom, our scientific intuition, predicted. But the results told a profoundly different story. Out of the 20 amino acids tested, an astonishing 11 showed complete stability. No reaction, no degradation. They remained perfectly intact in sulfuric acid concentrations that should by all accounts have annihilated them. 8 additional amino acids showed significant stability, even after undergoing partial chemical alteration, meaning they transformed into related compounds, but did not decompose into unrecognizable inert fragments. Only a single amino acid out of 20 showed significant instability and breakdown. Think about the staggering implications of this. 19 out of 20 amino acids either survived completely or survived in recognizable altered forms in sulfuric acid at Venus cloud conditions. These are not exotic molecules concocted in a lab. These are the very building blocks of life as we know it, and they can persist in Venus's clouds. This finding demolishes the long-held assumption that Venus's sulfuric acid instantly sterilizes all organic chemistry. It doesn't. Sulfuric acid, it turns out, is selective. It attacks certain molecular structures aggressively while leaving others remarkably essentially untouched. And here's the crucial link. The amino acids that survived are precisely the types of molecules that 3I Atlas was delivering to Venus on November 3rd. Hydrogen cyanide, upon breaking down in water, an acid readily forms amino acids and other organic precursors. Those products, the very ones arriving at Venus from this unique cometary chemistry, are now known to be stable in sulfuric acid at cloud temperatures. They don't get eliminated immediately. They persist. They remain available for further chemistry. They can actively participate in reactions, explore pathways toward complexity, and build more sophisticated molecular structures before photochemistry or circulation eventually brings them to regions where they finally break down. This changes the entire framework for understanding what happened on November 3rd. The hydrogen cyanide delivered by 3I Atlas didn't arrive and simply vanish. It arrived and immediately began a series of transformations, each step potentially producing stable or semi-stable products that can persist for meaningful timescales. When HCN dissolves in dilute sulfuric acid in Venus's upper clouds, it hydrolyzes, reacts with water, to break down into ammonia and formic acid. Ammonia is a base. In an overwhelmingly acidic environment, bases neutralize acid locally. They create microenvironments within the droplets, where the pH is elevated, where the acidity is reduced, where chemistry that simply couldn't occur in pure sulfuric acid suddenly becomes possible. These neutralized zonas, these chemical oases, are precisely where organic chemistry can be most active, where amino acids can form, where more complex molecules can assemble, without being immediately attacked by the surrounding acid. The sulfuric acid droplets therefore become tiny isolated chemical reactors, operating under conditions we never expected could support prebiotic chemistry. Each droplet contains a rich dynamic mixture sulfuric acid water, dissolved organic molecules from the Comet ammonia produced by HCN breakdown formic acid, and trace amounts of nickel compounds. An unprecedented cocktail. The chemistry inside these droplets is not static, not in equilibrium. Energy is being input constantly through solar radiation. Temperature fluctuations occur as droplets rise or fall through atmospheric layers, experiencing different thermal conditions. And crucially, the droplets are individual isolated microreactors. They are discrete reaction vessels floating in the atmosphere, so reactions in one droplet can proceed independently of what's happening in neighbouring droplets. This creates a massively parallel chemical exploration, where billions of droplets are simultaneously testing different reaction pathways, producing different products, exploring different possibilities. Some droplets will undoubtedly produce nothing of interest, just random combinations of molecules that don't lead anywhere chemically significant. But some droplets might by chance and sheer volume of experiments stumble onto pathways that produce more complex organics, small peptides formed from amino acids linking together, nucleotide precursors assembling from HCN-derived products, lipid-like molecules forming from reactions between organic acids. None of this constitutes life. None of this creates biology, but it represents complexity, chemical structures more sophisticated than simple precursors, exhibiting organization and patterns that don't occur in random chemical mixtures. It's precisely the kind of chemistry that astrobiologists study when trying to understand how life's fundamental building blocks could have emerged from non-living chemistry on early Earth or other worlds. And this is happening right now in Venus's clouds, not as a hypothetical future scenario, not as a mere possibility we might observe decades from now. This chemistry began the moment 3I Atlas's materials integrated into Venus's atmosphere on November 3rd. For weeks now, sulfuric acid droplets enriched with cometary organics have been circulating through Venus's upper atmosphere, reacting, transforming, and potentially assembling complexity. The photochemistry that will eventually destroy these molecules is also relentlessly underway. UV radiation is constantly breaking bonds and creating radicals, but the timescale for complete photochemical destruction is weeks to months. And during that critical window, the organic chemistry is profoundly active. Here's the piece that makes this even more remarkable. Venus's clouds have long been proposed as a potential habitat for hypothetical microbial life. Not because sulfuric acid is inherently friendly to biology, it absolutely is not, but because the specific conditions in Venus's upper clouds mirror certain parameters that life as we know it requires. Temperatures are moderate, liquid water exists in the droplets, albeit mixed with sulfuric acid. Sunlight provides energy. The clouds are stable enough that hypothetical microbes could potentially remain airborne, indefinitely circulating with the atmospheric flow. The main objection, the insurmountable barrier, has always been chemistry. What would these microbes eat? Venus's atmosphere doesn't naturally contain organic molecules in meaningful quantities. Any hypothetical life would have to synthesize everything from atmospheric carbon dioxide and nitrogen, which is an energetically expensive and extraordinarily difficult endeavour. But if Venus regularly receives a steady supply of complex organic chemistry from external sources, comets, meteorites, interplanetary dust, then the clouds would have access to raw materials that make the initial chemistry far less prohibitive. 3I Atlas just delivered a substantial bolus of exactly those raw materials, hydrogen cyanide, and its breakdown products amino acids and other organic precursors. If hypothetical microbes exist in Venus's clouds, they've just received an unexpected feast. If they don't exist, which is far more likely given the extreme conditions, the very chemistry that could lead toward their emergence has just been powerfully seeded. Does this mean life will suddenly appear? Absolutely not. The gap between complex organic chemistry and actual biology is enormous, involving countless additional steps and requirements. But the gap is unequivocally smaller now than it was before November 3rd. Venus's clouds are currently exploring chemical territory they don't normally access, courtesy of an interstellar visitor. The implications extend far beyond Venus. If sulfuric acid clouds can support prebiotic organic chemistry, if molecules can survive and react and build complexity in environments we thought were utterly sterile, then our understanding of where chemistry relevant to life can operate expands dramatically. acidic environments on other worlds become less immediately dismissible. Atmospheric chemistry in general becomes a more interesting venue for prebiotic processes. The universe's inventory of places where complex chemistry might emerge grows larger, and all of this stems from recognizing that Venus's sulfuric acid isn't the universal indiscriminate destroyer we assumed it was. It's selective. It preserves certain structures while aggressively attacking others, and the structures it preserves happen to include many of the fundamental building blocks necessary for life. That's not coincidence, it's chemistry. And chemistry, as we're learning, is far more permissive and creative than simplified models suggest. Venus's atmosphere is currently demonstrating that creativity processing materials from an interstellar comet, undergoing reactions that haven't occurred there in billions of years, and potentially producing complexity we won't fully understand until the observational data is analysed and published in the months ahead. Now let's discuss the ingredient that makes Venus's current atmospheric chemistry genuinely unprecedented: catalytic nickel. When refined nickel from 3I Atlas entered Venus's sulfuric acid clouds, it didn't just arrive as a passive trace element, a mere curiosity. Nickel is chemically active. It's one of nature's most effective catalysts, and its arrival at Venus introduces a capability the atmosphere has never possessed: the ability to accelerate specific reactions that would otherwise proceed so slowly they are for all practical purposes impossible. Understanding what nickel can do in Venus's clouds requires understanding catalysis itself, because this is where the story shifts from merely interesting chemistry to potentially transformative chemistry. Catalysts work by providing alternative reaction pathways that require significantly less energy than the uncatalyzed reaction. Think of a chemical reaction as climbing a formidable mountain. Reactants start in one valley, and products are in another valley on the far side. The uncatalyzed reaction requires climbing directly over the mountain, a high energy barrier resulting in agonizingly slow progress. A catalyst, by contrast, is like a tunnel through the mountain, a dramatically lower energy barrier enabling much faster progress. The catalyst doesn't change whether a reaction is thermodynamically favourable, it changes how quickly the reaction reaches equilibrium. In systems where reactions are thermodynamically favourable but kinetically hindered, meaning they should occur based on energy considerations but proceed too slowly to matter on any relevant timescale, catalysts make the impossible practical. Nickel catalyzes several reactions profoundly relevant to Venus's atmospheric chemistry. The most significant is the water-gas shift reaction, carbon monoxide plus water-producing carbon dioxide plus hydrogen. Venus's atmosphere now contains elevated concentrations of carbon monoxide delivered by the comet, and it contains water intricately mixed within the cloud droplets. Under normal circumstances, these molecules could coexist indefinitely without reacting significantly, because the activation energy for the water-gas shift is simply too high at Venus's cloud temperatures. But in the presence of a nickel catalyst, the reaction becomes viable. Nickel provides a surface or a specific coordination geometry where CO and water molecules can adsorb adjacent to each other, react, and swiftly release the products. The significance isn't immediately obvious until you think through the implications. Carbon dioxide produced through this reaction is denser than carbon monoxide. It subtly affects local atmospheric dynamics and slightly different buoyancy and pressure profiles in the droplet vicinity. Hydrogen produced is extremely light. It's the one molecule that can eventually escape Venus's gravity entirely if it reaches high enough altitudes. Hydrogen escaping from Venus represents a net loss of atmospheric mass, tiny on individual reaction scales, but potentially measurable if the catalyzed reaction proceeds extensively across many droplets. More importantly, hydrogen is highly reactive. Before it escapes, it can participate in reduction reactions where it donates electrons to other molecules. Sulfuric acid itself can be reduced by hydrogen in the presence of catalysts producing sulfur dioxide and water. Organic molecules can be reduced, altering their structures and producing different compounds with different chemical behaviours. Nickel also catalyzes Fischer-Tropsch type reactions. processes where carbon monoxide and hydrogen combine to form longer-chain hydrocarbons or other complex organic molecules. These reactions typically require high temperatures and pressures in industrial settings, but catalysts dramatically lower the required conditions, making them feasible in less extreme environments. Venus's clouds aren't ideal for typical Fischer-Tropsch chemistry by any means, but the presence of nickel CO and hydrogen creates the fundamental ingredients. In droplets where concentrations are elevated and temperatures happen to be favourable, perhaps in regions undergoing compression as air descends, the reaction might proceed at measurable rates. The products would be longer-chain organics molecules far more complex than the simple precursors delivered by the Comet. Beyond these specific named reactions, nickel catalyzes general condensation and rearrangement reactions involving organic molecules. If amino acids are present in a droplet alongside nickel ions, the nickel can facilitate peptide bond formation, the crucial linkage of amino acids into short peptide chains. If nucleotide precursors are present, nickel can catalyze their condensation into longer structures. This is precisely the role nickel-containing enzymes play in Earth biology. Enzymes are nature's biological catalysts, and many utilize metal ions, like nickel at their active sites, to scaffold and accelerate specific reactions. Venus's cloud droplets don't have enzymes, but they now have nickel ions dissolved in solution, and those ions can perform similar, though less efficient catalytic functions. The concentration of nickel in Venus's clouds after 3I Atlas's delivery is estimated at parts per billion levels. That's extraordinarily low by industrial standards, where tons of catalyst might be used. But biology operates at strikingly similar concentrations. Enzymes in living cells are typically present at parts per million to parts per billion concentrations, yet they drive all cellular chemistry with incredible efficiency. The key is turnover. A single catalyst molecule can facilitate thousands or even millions of reactions before being deactivated. Nickel in Venus's clouds has that same potential. A single nickel ion dissolved in a droplet can catalyze multiple reactions involving different molecules over the weeks. It remains active before the droplet precipitates, or the nickel reacts away into unreactive forms. The question becomes, does nickel catalysis in Venus's clouds actually produce measurable increases in chemical complexity? The theoretical answer based on known chemistry is a resounding yes. Catalysis accelerates reactions that are thermodynamically favourable but kinetically hindered. The practical answer depends on specifics. We don't yet know the exact concentration of nickel in individual droplets. The local concentrations of reactant molecules like CO and HCN-derived products, the precise temperature profiles droplets experience as they circulate, and the resonance time of nickel in catalytically active forms before it's oxidized or bound into unreactive compounds. These are parameters the Akatsuki data might reveal, or that sophisticated modelling studies can estimate. But the mechanism is sound. The chemistry is real. Nickel is present. The conditions allow catalysis. The only remaining question is scale. What makes this particularly fascinating is the profound parallel to how life uses catalysis. Every living cell, from the simplest bacterium to the most complex mammal, relies on metal catalysts, iron, nickel, cobalt, molybdenum, copper, to drive the chemistry that simply wouldn't occur fast enough otherwise. The origin of life almost certainly required access to catalytic surfaces, or metal ions that could accelerate the formation of more complex molecules from simple precursors. Venus's clouds, now enriched with nickel from an interstellar comet, are experiencing a version of that very process. Not biological, not intentional, not guided, but catalytic. And catalysis is one of the key mechanisms that separates complex chemistry from random mixtures of molecules. Venus's atmospheric chemistry was already interesting, because the organic precursors delivered by the comet can survive in sulfuric acid. Add catalysis, and it becomes more interesting still. Now, the chemistry isn't just surviving, it's being accelerated, organised, and pushed toward complexity at rates faster than purely thermal processes would allow. The sulfuric acid droplets circulating through Venus's upper atmosphere are operating as billions of tiny chemical experiments, each testing whether catalytic nickel can drive reactions that produce unexpected products. Most experiments will likely be null results, nothing interesting forms, but chemistry is fundamentally a numbers game. With enough parallel experiments, even low probability outcomes occur somewhere. And Venus is running this experiment at a massive scale across billions of droplets for weeks to months as the comet-delivered materials circulate and gradually photodissociate. The ultimate outcome is as yet unknown. We are not observing this in real time with direct molecular sampling. We are inferring what must be happening based on chemistry we understand and materials we know arrived. But the framework is clear. Venus's clouds are currently enriched with catalytic nickel prebiotic organic molecules and constant energy input from solar radiation. Those are the fundamental ingredients for chemical complexity. Whether that complexity actually emerges in measurable forms is what the data will ultimately tell us. But the possibility exists, and that possibility is being explored right now in Venus's atmosphere, whether we're watching closely or not. The chemistry doesn't wait for our instruments to be ready or our papers to be published. It proceeds according to its own immutable rules, and those rules now include catalysis provided by nickel from an interstellar comet. That's the true gift 3I Atlas gave Venus, not just raw materials, but the very tools to do something truly interesting with them. Venus responded by processing. The materials arrived on November 3rd directly into an active churning atmosphere. There was no cold surface to archive them. There was no stable ice to preserve them. The chemistry began immediately. Hydrogen cyanide started hydrolyzing into ammonia and formic acid within hours. Water mixed with sulfuric acid and profoundly changed cloud droplet composition. Nickel dissolved into acid solutions and acquired its potent catalytic roles. Atmospheric circulation distributed everything globally within days. Photochemistry began breaking down the novel molecules within days to weeks. Venus is an alchemist, a planetary transformer. It takes whatever arrives and immediately begins transforming it, processing it through relentless circulation and intricate chemistry, producing new compounds and gradually eliminating the perturbation as reactions proceed to equilibrium or photochemical destruction. The timescales are radically different from its inner solar system neighbour. Mars's interaction with 3I Atlas's delivery is measured in years. The materials deposited in October 2025 will remain largely unchanged, locked in the cold regolith, until robotic excavation begins in mid-2027, roughly 20 months of waiting. Even after excavation, the transformation will proceed over years, as industrial processes gradually convert regolith into useful materials. Venus's interaction, by contrast, is measured in weeks to months. The chemistry is active now. The transformations are ongoing. By January or February 2026, much of the comet-delivered chemistry will have been photodissociated or circulated to background concentrations. The perturbation will fade naturally, a transient but powerful event without external intervention. The mechanisms, too, differ fundamentally. Mars involves technology. The interesting interactions, the catalytic acceleration of reactions, the unexpected optimization of resource processing, the exploration of chemical complexity, all require sophisticated robotic systems to excavate and heat the materials. Absent human technology, Mars simply stores the comet's delivery indefinitely. Venus requires no technology. The atmospheric circulation, the cloud chemistry, the photochemistry, all are natural processes operating continuously. Venus explores the comet's chemistry through purely natural mechanisms. No robots needed, no excavation, no industrial heating, just planetary-scale atmospheric dynamics, doing what it always does, but now with novel ingredients. From an astrobiology perspective, both scenarios are fascinating for distinct reasons. Mars represents a hybrid scenario where spontaneous chemistry meets artificial acceleration. The question there is what happens when industrial-scale energy and AI optimization are applied to regolith that happens to contain prebiotic precursors and catalytic metals. Venus represents a pure, unadulterated natural experiment. Given prebiotic precursors, an active atmospheric system, and catalytic metals, does complexity emerge spontaneously, without technology, without excavation, without anything except planetary processes, operating on chemistry delivered from outside Venus tests? Whether atmospheric environments can serve as venues for the chemistry that might eventually lead toward life? The answer has profound implications for exoplanet studies. If Venus-like atmospheres can support complex organic chemistry, despite their apparent hostility, then atmospheric habitability becomes a broader, more inclusive concept than surface habitability alone. Neither scenario, let's be clear, produces life. Neither transforms Mars or Venus into instantly habitable worlds. But both involve chemical systems responding to external perturbation and exploring new territory. Both test the boundaries of where complexity can emerge, and both provide natural experiments we can observe, measure, and learn from. The fact that we're observing both simultaneously, Mars's slow storage and eventual technological interaction, Venus's rapid atmospheric processing, is historically unprecedented. We've never had the instrumentation and orbital presence at multiple planets to observe their distinct responses to the same external delivery in near real time. The comparative study, the grand scientific synthesis, hasn't fully begun yet. Mars data from October 3rd through late 2025 is still being processed. Venus data from November 3rd onward is being meticulously analysed. The synthesis papers comparing the two planetary responses, modelling what each system is doing with the delivered materials, interpreting what the differences teach us about planetary chemistry, won't appear until 2026. But the framework has established two planets, same source, radically different responses. One slow and technological, one fast and natural, both potentially revealing about how chemistry operates under extreme conditions when given external inputs. What emerges from this comparison is a recognition that planets are individuals. They don't respond uniformly to the same inputs. Their existing conditions, temperature, atmospheric composition, geological activity, magnetic fields, determine how they process external chemistry. Mars's cold inertness transforms it into a preservationist, archiving whatever arrives for future disturbance. Venus's dynamic atmosphere transforms it into a processor, immediately integrating and transforming external inputs through active chemistry. Neither response is inherently better or worse. They are simply different strategies for handling the same profound challenge: how to accommodate materials that aren't in equilibrium with existing conditions, and both responses are being documented by human spacecraft and ground-based telescopes. We're watching planetary chemistry unfold across multiple worlds simultaneously. The data is being collected, the observations are being recorded, the analysis will synthesize everything into a deeper understanding of what happened, why each planet responded as it did, and what the outcomes teach us about chemistry planets, and the potential for complexity to emerge when worlds receive gifts from interstellar space. The next year will bring those answers as publications emerge and the scientific community debates interpretations. Until then, we wait. But we wait knowing that the processes are active, the chemistry is real, and the story is profoundly unfolding. Whether we're fully observing it or not, Mars is holding. Venus is transforming. And 3i Atlas has given both planets materials they haven't encountered in billions of years, setting in motion processes that will occupy scientists and fascinate observers for years to come. We're standing at a specific point in time, late November 2025, and everything that's happened so far is prologue. The Comet encountered Venus just 3 weeks ago. The materials were delivered, the novel chemistry began, and now we're in the waiting phase, the critical period where raw observations transition to profound understanding, where data becomes published findings, where speculation gives way to confirmation or refutation. Let me walk you through what's coming over the next 18 months, because this timeline determines precisely when we'll have definitive answers to the pressing questions this entire story has raised. And those answers matter, not just for Venus, not just for Mars, but for how we fundamentally understand planetary chemistry and the potential for complexity to emerge in extreme environments throughout the universe. Right now, in late November 2025, ground-based observatories are continuing their diligent tracking of 3I Atlas as it slowly recedes from the inner solar system. The comet is still visible, still outgassing though, at gradually declining rates. Spectroscopic measurements continue documenting water, hydrogen, cyanide, carbon monoxide, and those tantalizing nickel emissions. These ongoing observations are absolutely critical for establishing baseline data. What was the comet producing after perihelion? How rapidly did its activity decline? What was the compositional stability over time? Major observatories worldwide, from the Swift telescope to the twin Keck observatories, are collectively building a complete activity profile for 3I Atlas that will anchor all subsequent analysis of what the comet delivered to our planets. Simultaneously, JAXA's Akatsuki orbiter has completed transmitting the bulk of its precious Venus encounter data back to Earth. Venus orbiters with their limited communication bandwidth due to distance require weeks to downlink a complete dataset from several days of intensive observations. By early December 2025, the data should be fully received at JAXA's mission control centers in Japan. Then begins the slow, methodical, painstaking process of calibration and analysis. Raw instrument data must be meticulously corrected for instrumental effects, calibrated against known standards and processed into scientifically usable formats. This is not fast work. It is careful, detail-oriented analysis by dedicated teams of scientists, ensuring unimpeachable data quality before even attempting interpretation. Preliminary results might emerge by late December, perhaps a tantalizing hint, but comprehensive analysis will extend well into January and February 2026. What will that data show if the theoretical framework we've outlined is correct? Akatsuki's spectrometers should detect elevated concentrations of water, vapor hydrogen, cyanide, or carbon monoxide in Venus's upper atmosphere during and immediately after the November 3rd encounter. The increases would be subtle, parts per billion changes in trace gas concentrations, but detectable if instruments were operating with sufficient sensitivity and were looking at the right atmospheric regions. If nickel compounds were present in sufficient quantities, they might show up in particle composition data or through unique spectral signatures from cloud droplets. If the data shows no significant changes, it indicates either lower capture efficiency than models predicted, faster photochemical destruction than expected, or instrumental sensitivity limitations that prevented detection. Any outcome importantly teaches us something valuable about Venus's atmospheric response to external inputs. January through March 2026 is when the first scientific publications will begin to appear. These groundbreaking papers will be submitted to prestigious journals like Icarus Geophysical Research Letters, Nature Astronomy, or similar planetary science venues. Initial submissions might even appear on preprint servers like ARChef in late December 2025, allowing the broader scientific community early access to findings before formal peer review completes. These papers will address specific foundational questions. Did atmospheric composition change measurably? Were HCN or CO signatures definitively detected? What do cloud droplet composition measurements reveal? How did atmospheric circulation distribute any captured materials? These initial papers won't answer every question, but they will establish the observational foundation for everything that follows. Simultaneously, detailed analysis of Mars orbital data from the October 3rd encounter will be published. NASA's Mars Reconnaissance Orbiter and ESA's Mars Express will have been collecting data for over a month by this point, meticulously documenting the southern highlands and polar regions where 3I Atlas's material should have deposited. Spectroscopic measurements from these orbiters can detect nickel enrichment hydrogen cyanide signatures in ice, or other indicators of cometary material deposition. If confirmed, these papers will validate the Mars deposition model. If signatures are absent or below detection limits, they'll force refinement of capture efficiency estimates, and deposition modelling pushing our understanding further. The media landscape will inevitably shift during this January to March window. Scientific findings will be translated into popular science articles and news coverage reaching beyond the academic community. The narrative of an interstellar comet fundamentally altering two planetary atmospheres will enter public consciousness more broadly. Some coverage will be accurate and measured, some inevitably will be sensationalized. Science communication is always a mixed landscape, but the core story, that external chemistry from an interstellar object has perturbed Mars and Venus in measurable ways, will gain wider recognition. Public interest, importantly, often drives further observation and funding for follow-up studies. So this media phase, while imperfect, serves an important function in maintaining scientific momentum. April through June 2026 brings the crucial phase of synthesis and modelling. With observational papers published and data widely available, researchers will begin building sophisticated computational models, exploring what the observations truly mean. What specific chemical reactions should have occurred in Venus's clouds given the observed concentrations? How long should comet-delivered materials persist before photochemistry destroys them? What products should form? How do atmospheric circulation models predict the distribution patterns? These modelling papers complement the observational papers, building a complete iterative picture where theory and observation constrain each other. Discrepancies between models and observations are not failures. They are powerful pointers highlighting areas where our understanding is incomplete and where further research is urgently needed. This is also the period when mission planners begin incorporating new findings into future mission designs. ESA and NASA, for instance, are actively developing concepts for future Venus missions. Potential orbiters with even more advanced spectrometers, possible atmospheric entry probes, and even long-shot sample return concepts. If the 3I Atlas encounter revealed unexpected chemistry in Venus's clouds, future missions might be retargeted to study those regions, specifically adapting to new knowledge. Similarly, Mars mission planning for post-2027 surface operations will meticulously incorporate an understanding of how the October 3rd deposition affected regional regolith chemistry. Science is an iterative process. Observations inform future observations, and understanding builds progressively. The mission proceeds according to its established architecture, but mission scientists are now acutely aware that the landing region might contain chemical signatures from the October 2025 Comet encounter. That knowledge informs what measurements to prioritise once systems are operational on Mars. By early 2027, the scientific community will begin to coalesce around a consensus on the broad strokes, while documented disagreements on details will still be under active investigation. On Mars, the data flowing back to Earth, efficiency metrics, yield rates, processing throughput, will tell the story indirectly even before scientists explicitly realise the connection. Engineers will start to notice subtle anomalies. Why is water extraction 8% more efficient than simulations predicted? And eventually someone will correlate those anomalies with the October 2025 Comet encounter. June 2027 onward is the operational phase where long-term patterns emerge. Months of Mars surface operations will generate datasets large enough for robust statistical analysis. If comet-delivered materials are indeed affecting processing chemistry, the signal will become unequivocally clear as noise averages out. Publications will appear documenting unexpected findings, enhanced catalytic activity in Mars, regolith processing, or the definitive detection of interstellar organic signatures in pulverized samples. The Mars and Venus stories that began in October and November 2025 will by this point reach their conclusion, or more accurately, reach the point where observations definitively confirm or refute the speculative framework we've so carefully built. Simultaneously, Venus atmospheric monitoring will continue. Follow-up observations by Akatsuki or future missions will check whether Venus's atmosphere has returned to its baseline composition, or whether lingering, more persistent signatures of the comet encounter remain. If organic molecules or unusual chemical patterns are detected months after the encounter, it suggests longer persistence timescales than predicted and raises profound questions about Venus's capacity to support complex chemistry for extended periods. Scientists will comment on papers, share interpretations, ask new questions. Science advances through collective scrutiny and rigorous discussion. The more people paying attention, the faster insights emerge, and the more thoroughly findings are examined for errors or alternative explanations. You are not a passive audience to this story. You are part of the global community making sense of what an interstellar comet did to 2 planets in our solar system. This is real science unfolding in real time. The data exists. The observations were made. The chemistry is happening right now whether we're watching or not. Over the next 18 months, speculation will give way to confirmation, and we'll know definitively whether 3I Atlas changed Mars and Venus in the precise ways theory predicts. The comet arrived from beyond our solar system carrying materials forged in another stellar environment billions of years ago. It passed through our inner solar system for a few brief weeks and delivered those materials to 2 planets with radically different environments. Those planets are now processing that delivery, one slowly through storage and eventual technological excavation, one rapidly through active atmospheric chemistry. Both are teaching us invaluable lessons about planetary systems, about chemistry under extreme conditions, and about how complexity can emerge when worlds receive gifts from interstellar space. Stay curious, stay engaged. The answers are coming, and when they arrive, we'll understand not just what 3I Atlas did, but what planets do when they encounter chemistry from beyond their own systems. Chemistry that hasn't been part of their evolution. Chemistry that forces them to respond, adapt, and explore pathways they've never travelled before. That's the story we're living through. That's the discovery unfolding across the solar system right now. And you're here at the beginning watching it happen.